Tonight, we're going to explore one of the most misunderstood challenges in modern spaceflight. More than half a century has passed since humans first walked on the moon, so it's easy to assume that going back should be straightforward. We've already done it. The landing sites are mapped. The footprints are still there, untouched in the lunar dust. So why has returning proven so difficult? The answer isn't that we've forgotten how to get there. It's that Apollo was never designed to be repeated. It was an extraordinary achievement built for a single moment in history, driven by an unprecedented political rivalry and supported by a level of funding that has never existed before or since. When that moment ended, much of the technology, infrastructure, and industrial capability that made the moon landings possible disappeared with it. Today, returning to the moon means solving an entirely different problem. Not simply landing astronauts once, but building a system that can do it again and again, safely, affordably, and sustainably. By the end of tonight, you'll understand why repeating Apollo isn't really an option, why returning to the moon is far more complicated than following old blueprints, and what it truly takes to establish a lasting human presence beyond Earth. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why, you have to understand what Apollo actually was. Not a space program in the conventional sense, but an emergency. The Cold War had turned the night sky into a scoreboard, and the United States was losing. The Soviet Union had launched Sputnik, put the first human in orbit, and strung together a run of early firsts that rattled American confidence to its core. What followed was not a sustainable plan for exploring space. It was a sprint to prove a point. At its peak, NASA received roughly 4.4% of the entire United States federal budget. Think about what that means. Not 4.4% of the science budget, not 4.4% of discretionary spending, 4.4% of everything the federal government spent. That translated to more than $25 billion in the money of the 1960s. Adjusted for inflation, more than $150 billion. All of it concentrated into a single symbolic program whose real purpose was to plant a flag before the other side could. No government on Earth funds science that way during peacetime. Not before and not since. Here's where it gets strange. The moment the goal was achieved, the funding evaporated. The flag went in on July 20th, 1969. Within a few years, the Saturn V production line was shutting down. Missions were cancelled. The Apollo applications program, which had hoped to turn the moon infrastructure into something lasting, was quietly dismantled. The political emergency that had generated the money was over. And without that emergency, the money stopped. This is not a failure of vision. It is simply what happens when a crisis-funded program achieves its crisis-level goal. The funding was never meant to last. The program was never designed to be sustainable. Apollo was a single extraordinary effort compressed into a decade by an external threat. Not a foundation, not a staircase, a sprint. And when the sprint ended, the sprinters went home. That is the first layer. But the second layer goes deeper, and it is in some ways harder to recover from. Funding can return. Political will can return. What cannot return so easily is something more physical. The machines are gone, and so are the people who knew how to build them. The Saturn V remains, to this day, the most powerful rocket ever successfully flown to orbit. At liftoff, it produced roughly 35 million newtons of thrust. To put that in terms you can feel, it could lift approximately 140,000 kilograms to low Earth orbit. That is about 310,000 pounds. The equivalent of roughly 25 fully loaded school buses launched to the edge of space in a single burn. No Saturn V exists in flight-ready form today. The ones that survive are museum pieces, horizontal and static, their engines cold. The factories that built the Saturn V's stages were shut down after the program ended. The specialized tooling, the fixtures designed for no other purpose, the precision jigs that held components in alignment during assembly were scrapped. The companies that supplied the parts merged with other companies, shifted their focus to different industries, or simply ceased to exist. The industrial ecosystem that had produced the Saturn V was not preserved. It was dissolved. Wait, surely the blueprints survived? They did. Many of them still exist. But here is what the blueprints cannot tell you. They cannot tell you which welds were temperamental. They cannot tell you which valve assemblies had a tendency to stick in cold temperatures, and what the technicians learned to do about it. They cannot tell you which test data to trust, and which numbers came from instruments that were known to read slightly off. They cannot tell you the feel of a component that was assembled correctly versus one that looked right but would fail under load. That knowledge was never written down. It lived in the people, in the hands of the welders, the judgment of the machinists, the instincts of the test engineers who had spent years running engines on stands at Stennis and Rocketdyne. Those people have retired. Many of them have died. The knowledge went with them. Think about a language that has no written form. When the last fluent speaker is gone, the grammar books and vocabulary lists that remain can tell you the words. They cannot tell you how the language breathed, how the rhythm of a sentence felt, which constructions a native speaker would have found awkward even if they were technically correct. Some of that can be reconstructed, slowly and imperfectly, but you are no longer recovering a language, you are building a new one. That is what rebuilding Saturn V hardware would actually require, not a manufacturing run using existing knowledge. A reconstruction from first principles with different suppliers, different materials, different regulatory frameworks, different workforce training standards, and a different understanding of which shortcuts are acceptable. The result might eventually fly, but it would not be a Saturn V. It would be a new rocket with old branding. Effectively, a new program. And that means anyone who wants to return to the moon sustainably cannot simply reverse the decision to stop going. The infrastructure has to be rebuilt from scratch. The industrial base has to be recreated. The human knowledge has to be re-earned. None of that is impossible. But none of it is the simple continuation that the phrase "going back" implies. The capability was not paused, it was ended. And the gap between those two things turns out to be the central problem. That is where the modern programs begin. Not with a blank slate, but with a deficit deeper than most people realize going in. Set the institutions aside for a moment. Set aside the funding gaps, the lost engineers, the dismantled supply chains. Go one layer deeper to where none of that matters. Down to the equations. The same physics that constrained Apollo is still there, unchanged, indifferent to budget lines and political will and engineering talent. It was there when Armstrong and Aldrin lit their descent engine in July 1969. It is there now, and it will be there for every crew that attempts the journey after them. The place to start is delta V. The term means change in velocity, and it is the single number that captures how hard any mission is. To get from the ground to low Earth orbit, a rocket must accelerate to roughly 7.8 kilometers per second. That is about 28,000 kilometers per hour, close to 7,500 miles per hour. But accounting for gravity drag and atmospheric losses, the engines must actually deliver closer to 9.4 kilometers per second of push just to reach orbit. Nothing has happened yet. The crew is circling Earth in a parking orbit, and the rocket has already burned most of what it started with. The next burn, the translunar injection, pushes the spacecraft out of that orbit and onto a path toward the moon. That costs another 3.2 kilometers per second. Roughly 7,200 miles per hour of additional velocity, added in a single firing that lasts only a few minutes. Then come more burns. Lunar orbit insertion to slow down and be captured by the moon's gravity. Powered descent to the surface. Ascent back to orbit. The return trajectory. Re-entry. Each burn must be controlled precisely. An error of a few hundred meters per second in the wrong direction can mean skipping off the moon's orbital plane, crashing into the surface, or arriving at Earth on the wrong trajectory entirely. The total delta V for a complete moon mission and return runs to roughly 10 or 11 kilometers per second, with margin. That number does not sound large. It is enormous. Here is why. Chemical rockets, the only kind powerful enough to lift astronauts off Earth, top out at a certain efficiency. There is a ceiling on how much thrust they can extract from burning fuel. Because of that ceiling, the only way to hit the required delta V numbers is to carry enormous quantities of propellant. For every kilogram of astronaut, life support equipment, and supplies, a rocket needs many tens of kilograms of propellant spread across all its stages. And the penalty is recursive. Adding more fuel adds more mass. More mass means the engines must work harder. Working harder means burning more fuel. Burning more fuel means carrying even more of it. The weight grows on top of itself. Think about a long hike where you must carry all your water. Carrying extra water adds weight, which increases how hard you work, which means you need more water for the effort of carrying the extra water. The math turns against you. For rockets, the math turns against you much faster and more severely. The solution is staging. As each section of the rocket exhausts its fuel, the empty tank and engines are jettisoned. Dead weight is dropped. But staging has limits too. Only a small fraction of a fully fueled moon rocket is the actual crew vehicle and lander that reach the moon. Everything else is fuel and empty hardware that gets discarded on the way. Earth's escape velocity is about 11.2 kilometers per second, roughly 25,000 miles per hour. The moon's escape velocity is only about 2.4 kilometers per second, around 5,400 miles per hour. A moon mission is a climb out of a deep gravity well, a fall into a much shallower one, and then a climb back out again to return home. The physics does not care how good the engineering is. The wells are fixed. The margins this creates are thin. A lander overweight by 300 to 400 kilograms, roughly 3 or 4 adult humans worth of mass, can exceed what the descent engine and fuel reserves can handle. The line between a successful landing and an aborted one can be that narrow. Apollo 11 made that line visible. The crew came down off course. The planned landing site was cluttered with boulders. Neil Armstrong took manual control and flew the lander sideways, searching for a clear patch of ground. Every second of hovering burned fuel the mission plan had not budgeted for extended search time. They touched down with roughly 15 to 20 seconds of usable fuel remaining. Not minutes, seconds. Had Armstrong needed another half a minute to find safe ground, the mission would have required an abort. Not a narrow margin, a razor margin. And that was on a mission with a crew who had trained for years for exactly that scenario. Modern crewed landers will need larger safety buffers. Larger buffers mean more propellant. More propellant feeds the recursive penalty all over again. But the reality is different. Even perfectly calculated fuel loads do not solve the fundamental problem of landing, because the moon offers no help at all on the way down. There is no atmosphere. Not thin atmosphere. None. On Earth, parachutes do most of the deceleration work. On Mars, even the thin air gives a falling object some drag to work with. On the moon, the only force slowing a descent vehicle is continuous engine thrust. From the moment the lander begins its drop from orbital velocity until the moment the legs touch the surface, the engines must fire without interruption. Too steep a descent angle, and the engines must kill too much horizontal speed too quickly. A guidance glitch at that point causes a hard impact. Too shallow, and the lander risks skimming the surface or bouncing back into a low, uncontrolled arc. The descent path is planned to within tens of meters and precise seconds of timing, then corrected in real time by radar as the vehicle falls. Earth cannot help in the final moments. The round-trip signal delay between Earth and the Moon is about 2.5 seconds. A command sent from a controller's hands takes 2.5 seconds to arrive. Any response takes another 2.5 seconds to return. That is 5 seconds of loop time. A descent vehicle moving at hundreds of meters per second can cover enormous ground in 5 seconds. Real-time joystick control from Earth is not possible. The onboard computer and crew handle the final approach essentially on their own. Any software error or sensor misread in those final minutes can end the mission in the lunar soil. The surface itself compounds this. Lunar regolith, the layer of fragmented material covering the moon, is not like sand or gravel on Earth. The particles are often smaller than 50 micrometers, less than 1/20th of a millimeter. They are jagged and irregular, shaped by billions of years of micrometeorite impacts in a vacuum, with no wind or water to round their edges. When a descent engine fires above the surface, The exhaust plume throws this material outward at hundreds of meters per second, fast enough to sandblast landing legs, fast enough to coat cameras, windows, and solar panels with an abrasive film that does not brush off, fast enough to erode equipment on the surface nearby. Dust thrown at that velocity behaves less like a cloud and more like a spray of microscopic shards. Scaling the problem up makes every one of these pressures worse. Apollo landers carried payloads measured in hundreds of kilograms. Cargo landers for a functioning base would need to deliver 10 to 20 metric tons at a time, between 22,000 and 44,000 pounds of equipment and supplies per mission. The rocket equation does not scale linearly with payload. Doubling the mass delivered to the lunar surface can more than double the propellant required, because heavier vehicles also need heavier structure, and heavier structure requires still more fuel to move. A single Apollo landing was expensive. A program of regular cargo deliveries, repeated many times a year, pushes the fuel math into territory that makes even ambitious modern programs strain. Apollo could afford a design philosophy of using something once and discarding it. That works for flags and footprints missions. It does not work for a base that needs to be supplied and maintained over years and decades. The physics was hard in 1969. It is equally hard now. And the institutional deficit covered in the previous section means modern programs are attempting to reclimb this mountain without the running start Apollo had. The raw equations are only the floor. Above that floor, everything else stacks. So what does that sustainable program actually look like? That is the question the physics leaves open. And when you examine it honestly, the answer is uncomfortable. Because the goal itself has shifted. Not the technology, not the budget. The definition of what success even means has changed, quietly and completely, since 1969. Start with what Apollo actually required. The mission definition was narrow. Land on the surface, walk, collect samples, return alive. That was it. At the time, that was considered more than enough. It was a historic achievement by any measure, and no one was wrong to treat it that way. But consider how that same mission would be received today. If Artemis landed 2 astronauts on the lunar surface, had them walk for a few hours, collected rocks, and brought everyone home safely, the program would be considered a short demonstration, a proof of concept, not a completed program. The bar for what counts as success has moved so far that repeating Apollo would not satisfy the mandate modern space programs are actually working toward. The goalposts are not just farther away, they are in a different field. The modern vision requires long-term human presence, not a visit, a foothold. Testing whether water ice buried in permanently shadowed craters near the poles can be extracted and turned into usable water and breathable oxygen. Building habitats that can sustain people through the 2-week lunar night when temperatures plunge and solar power disappears. Installing power grids, deploying long-duration rovers, developing the early infrastructure that might eventually resemble a functioning outpost rather than a campsite. And behind all of that is Mars. Not as a metaphor, but as an explicit planning horizon. The moon is meant to be a proving ground, a place to learn how to keep people alive for months or years away from Earth before attempting the much longer journey to the next planet. Everything built on the moon is, in a sense, a rehearsal. That raises the stakes for every system, every test, every margin of error. A failure mode that would be acceptable during a short visit becomes unacceptable if the goal is a sustained operation. Think about the difference between summiting a mountain once and building a permanent station on it. The summit is an achievement. The station is infrastructure. The summit rewards courage and preparation. The station rewards engineering, supply chains, maintenance schedules, redundancy, and the kind of institutional patience that is almost the opposite of a sprint. Here is where the second shift compounds the first. Because it is not only the goal that has grown, the conditions under which modern programs must achieve it have tightened in the opposite direction. NASA's budget share is far smaller than it was during Apollo. Public patience for long timelines is lower, and safety expectations are higher. Not slightly higher, categorically higher. The mandate is to do more, with less, under harsher scrutiny, over a longer time horizon. That combination does not make the challenge incrementally harder. It makes it structurally different. Some of that pressure comes from a reasonable assumption. The assumption goes like this: start with robotic missions, prove the systems, then add humans later. It sounds prudent, but it rests on a confusion about what human rating actually demands. A cargo rocket can tolerate a certain failure rate. If a rocket carrying equipment to the moon fails on ascent, the cost is real. Hardware is lost. Money is lost. The mission is set back. That is painful, but it is recoverable. The system continues. Add humans to that vehicle and everything changes. Not incrementally, categorically. A human-rated rocket requires a launch escape system. This is a mechanism capable of pulling the crew capsule away from the main vehicle within milliseconds if a catastrophic failure begins during ascent. That system has its own propulsion, its own guidance, its own triggering logic, and it must work reliably in the worst possible moment. When something is already going wrong, it is not a feature. It is an entirely separate capability integrated into the vehicle. That is just the beginning of what changes. Guidance systems need backups. Communication systems need backups. Power systems need backups. Life support must maintain oxygen levels, carbon dioxide concentration, humidity, and temperature not for a few hours but for days to weeks, depending on mission phase. Abort options must exist at every point in the mission. During ascent, during the burn that sends the crew toward the moon, during lunar orbit insertion, during descent, at every phase where something could go wrong and the crew would need a path to survive. Each of those abort scenarios is not a theoretical footnote. Each one requires a specific plan, supporting hardware designed around that plan, and trained crew responses practiced until the responses are automatic. The vehicle has to be designed so that the abort path never requires the vehicle to be working correctly. It has to work when things are broken. That is a different design philosophy from the ground up. This is what human rating means. It is not adding seats to a cargo rocket. It is rebuilding the entire design process around a new constraint, one that touches every subsystem, every test protocol, every verification standard. The cost, time, and complexity that result are not overhead. They are the mission. None of this is an argument against going back. It is an argument for clarity about what going back actually involves. The physics is the same as it was in 1969. The rocket equation has not changed. Lunar gravity has not changed. The distance has not changed. But the definition of the goal has changed. And the conditions for achieving it have changed. And the safety framework for carrying humans has changed. The floor was already hard. Above that floor, the challenge has only grown. And the programs attempting to clear it are doing so without the institutional running start that made Apollo possible in the first place. What that looks like in practice, what it means to engineer all of this simultaneously, is where the story goes next. So what does a modern program actually have to build with? The first instinct is to reach for what already worked. The Saturn V flew 12 times. It carried astronauts to the moon. The blueprint survived. The engineers who built it were brilliant and their drawings are detailed. The argument writes itself. We did this before. We have the documentation. We build it again. But something was wrong. The blueprints are not Lego instructions. They are records of decisions made by people who already understood everything the documents took for granted. Think about a recipe passed down through 3 generations of cooks. The recipe exists on paper. The ingredients are listed. The temperatures are written down. But the cook who wrote it knew without writing it which flour to use, how the dough should feel when it is ready, when to trust the instructions, and when to adjust for humidity. That knowledge never made it onto the page. You can follow the recipe exactly and still not produce the same dish because you are missing everything the cook already knew before picking up the pen. The Saturn V blueprints have the same problem. They specify welds, but the notation assumed the welder already knew the temperature sequence and the hand technique behind it. They specify alloys, but the mill that produced them has been closed for decades. They specify valves and seals whose original vendors retired their manufacturing lines in the 1980s and 1990s. The documents assumed a living context. That context is gone. Saturn V was not a product. It was a national emergency scaled into engineering. The rocket stood about 110 meters tall, roughly the height of a 36-story building. Fully fueled, it weighed around 2,900 tons, close to 6.4 million pounds. Behind it sat thousands of companies and hundreds of thousands of workers spread across the United States, synchronized to a single political objective: reach the moon before the Soviet Union. That was not a sustainable industrial program. It was a crisis mobilization wearing the clothes of a space program. When Apollo succeeded, the political emergency ended. Budgets fell, contracts were cancelled, the workers moved to other industries. The tooling, the jigs, the specialized manufacturing lines, the accumulated judgment of the technicians who knew which welds ran temperamental and which instruments read slightly off, none of it was preserved. It was allowed to dissolve. Rebuilding from those blueprints today would not be a reconstruction. It would be a new design program carrying the additional burden of matching old specifications that were never written down completely. Every material would need to be requalified. Every weld would need to be redeveloped. Every engine would need to be retested. Every supply chain would need to be rebuilt from scratch. What people imagine as pulling a known answer off a shelf is, in practice, designing a new rocket under constraints that the original designers never faced. That is not a revival. It is a harder version of starting over. And there is a second problem layered on top of the first. Even if someone reconstructed the Saturn V exactly, it would fail modern certification. Apollo flew in an era of different standards. The vehicle used materials we now consider hazardous, including asbestos in insulation and toxic chemicals in sealants. Its wiring, its fault tolerance, and its software validation methods were developed before modern human rating frameworks existed. An Apollo-era design submitted for certification today would require redesigned fire suppression, full electronics redundancy, and software verification processes that did not exist when the original vehicle was built. The resulting vehicle would carry Saturn V's silhouette. It would not be Saturn V, it would be something new, shaped by the ghost of something old. So the blueprints do not offer an easy path, but a different instinct is also available. Modern rockets exist, lots of them. Falcon 9 has flown more than 300 times. Falcon Heavy can lift substantial payloads. Ariane 6, Long March, New Glenn. The launch cadence of the modern commercial industry is something the Apollo era never achieved. Why not use what already works? Wait, these rockets were designed for a completely different destination. Their market is low Earth orbit, roughly 400 kilometers above the surface, and geostationary transfer orbit, roughly 36,000 kilometers out, where communication satellites, weather systems, GPS constellations, and Earth observation platforms live. Their designs are optimized for those customers. Payload fairing size, cost per kilogram, reuse cycles, launch cadence, the entire engineering logic of those vehicles flows from the satellite market. That is the problem they were built to solve. The moon is approximately 384,400 kilometers away. That is nearly 1,000 times farther than low Earth orbit. A lunar mission is not a scaled-up satellite launch. It requires a vehicle with enough payload capacity to carry a crew capsule, a lander, propellant for the lunar orbit insertion burn, propellant for the descent, propellant for the ascent back to orbit, and propellant for the return to Earth. It may require orbital refueling. It may require assembling mission elements launched on multiple vehicles before any of them goes anywhere. A delivery van is well designed for the route it runs. You would not use it to relocate a house. The engineering logic is different at the root. This is why the United States is not pointing at an existing commercial rocket and declaring the moon mission solved. The Space Launch System, developed under the Artemis program, is designed to lift roughly 70 to 130 tons to low Earth orbit, around 154,000 to 286,000 pounds, which puts it in Saturn V territory for raw lift capacity. It reuses engine hardware derived from the Space Shuttle program, wrapped in new tanks, new structures, and new avionics. The Orion capsule is the new crew vehicle, various lander concepts, both commercial and government developed, are being built in parallel to handle the final descent and ascent from the lunar surface. None of this is bringing back Apollo capability. It is building a new industrial base from scratch in a different era, under pressure to be cheaper and safer at the same time. The physics from earlier sections has not softened. Every kilogram of that 130-ton lift capacity has to be earned through the same rocket equation. Every bolt and cable and line of code has to survive supply chains, safety reviews, funding cycles, and shifting political priorities. The constraints are not easier than they were in 1969. In most respects, they are harder. And unlike Apollo, there is no political emergency generating unlimited resources and institutional will to burn through every obstacle in sight. The programs moving forward are doing so with the tools they can build under the conditions that actually exist. The question of what those programs can realistically achieve and on what timeline is where the harder accounting begins. That harder accounting does not start with engines or orbital mechanics. It starts somewhere else. It starts with the question of whether the political system has any real intention of underwriting the work at all. Money and attention behave like their own kind of gravity well. They pull programs downward. They resist the energy required to stay in motion. And understanding why requires looking at what happened the last time humans reached the moon. Because the lesson from Apollo is not what most people expect. The assumption in 1969 was that once humans planted a flag on the lunar surface, public support would lock in. The achievement would demonstrate what was possible. Budgets would follow. The program would build on itself. The opposite happened. After Apollo 11, public interest dropped rapidly. By Apollo 12, TV networks were already cutting away from live coverage. Viewers had seen the moon. They had watched a man walk on it. The second mission felt like a repetition. By Apollo 13, attention had lapsed so completely that the oxygen tank explosion and the near loss of 3 astronauts became the event that drew audiences back, not the mission itself. A disaster restored the drama that routine success had already exhausted. Apollo 17 flew in December 1972 and became the last lunar landing. No Apollo 18, no Apollo 19. The program was over. NASA's budget share at its Apollo peak reached roughly 4.4% of the entire federal budget. Within a few years of the first landing, it was falling hard. It has stayed well under 1% ever since. The paradox is sharp. The more normal the moon began to feel, the less willing the public was to pay for it. Familiarity did not build support. It dissolved it. A modern lunar program walks into that legacy, and the financial reality it faces has not improved. A single flagship mission, counting development, hardware, launches, and operations, can reach $10 to $20 billion on its own. A sustained return program, spread across 10 to 20 years, runs into the tens of billions in total. That is not a number drawn from a single budget line. It competes every year against healthcare funding, defense procurement, pension obligations, education, infrastructure, and climate programs. Each of those priorities arrives with strong lobbies and visible daily impact. A hospital wing is something a legislator can point to. A lunar ascent stage is harder to sell to someone whose district needs a bridge. When resources tighten, and they do tighten, space programs look trimmable. Nothing collapses tomorrow if a lunar budget is cut. The program weakens slowly over years, through 100 small decisions that each seem manageable. The picture did not hold. Even when funding survives, the program can be undermined from within the political cycle. The start-stop pattern has become one of the defining features of American human spaceflight since Apollo. Constellation was announced as the vehicle family that would return humans to the moon. It was reworked, scaled back, and eventually cancelled. The Space Launch System and Orion capsule emerged from that shuffle, carrying some of the same heritage hardware, shaped by the same institutional pressures. Artemis was then layered on top as the new branding for lunar return, reorganizing the goal again around a revised architecture and a revised timeline. Each restart wastes something that cannot be easily recovered. Engineering knowledge, software, test data, the hard-earned understanding of what works and what does not. Teams disperse when a program is cancelled. Contractors lose staff. Younger engineers watch years of their work vanish under a new administration, and some of them leave. The ones who stay carry a learned skepticism. They have seen a program cancelled before. They know the target can shift. That knowledge changes how they work. Internal progress slows, not because of any single decision, but because trust in the plan erodes quietly and continuously. Think about building a tall tower. You lay the foundation. You frame the lower floors. You work upward floor by floor. Then someone orders a redesign. You tear down what you built and start over with new specifications. You get a few floors up again. Another administration arrives. Another redesign. The tower never rises past a certain height, not because the engineering is impossible, but because the rebuilding consumes the time that ascent would have used. That is the structural damage that program discontinuity inflicts. It is not visible in any single budget line. It accumulates quietly, year by year, inside the organizations carrying the work. There is a second force pulling in the same direction. Society's tolerance for risk has changed since Apollo, and the change runs deep. In 1986, the Space Shuttle Challenger broke apart 73 seconds after launch. 7 crew members died. The disaster played out live on television and was replayed thousands of times in the days that followed. In 2003, the Space Shuttle Columbia disintegrated during a re-entry. Another 7 crew members died. Between those 2 accidents, 14 astronauts were lost. Both investigations were long, public, and technically specific. The coverage was not limited to a news cycle. It became part of how an entire generation understood what spaceflight costs. The moon itself has not become safer. The vacuum is still absolute. The dust is still jagged and abrasive. The landing dynamics still require a powered descent from orbital velocity with no atmosphere to assist. None of those physical facts have changed, but the public and political expectation has shifted towards something closer to zero risk. A single fatal accident on a lunar mission today, playing out live on screens across the world, could freeze human spaceflight for years. Programs respond to that expectation with more redundancy, more testing, more safety reviews, more backup layers at every stage of development. That response is rational. The tension it creates is real. More caution means more cost and more time. More cost and more time mean more budget cycles, more political exposure, more opportunities for cancellation. The solution to risk creates new versions of the same underlying problem. And even when a program survives all of that, it faces something subtler. The return on investment from lunar exploration is real, but it is diffuse. It is slow. It does not show up in ways that map cleanly onto budget hearings. Think about what it means to invest in something whose benefits scatter across decades and across millions of people who will never know what caused them. Lunar programs generate technology spin-offs, new materials, new software, medical advances drawn from life support research, improvements in communications, and a pipeline of trained scientists and engineers who carry that knowledge into other fields. They contribute incremental steps toward the long horizon goal of sustaining human life beyond Earth. Every one of those benefits is real. None of them can be pointed to cleanly. No one can hold up a single product and say with certainty that it exists only because of that mission. The connection is diffuse across time and across institutions. Compare that to a bridge, or a hospital, or a tax reduction. Those deliver in ways voters can observe and attribute. Space exploration delivers in ways that require a much longer view to see it all. When budgets tighten, the diffuse return is the first thing cut. Nothing breaks visibly when the lunar program loses funding. The silence of a slow failure looks like fiscal responsibility. That is the gravity well, not the one the rocket has to climb out of. A second one, built from public attention that peaks and falls, from budgets that compete against visible urgency, from program restarts that consume accumulated momentum, from risk tolerance that has fallen without the physical danger falling with it, and from returns too scattered to defend in any single budget cycle. Each of those forces is modest on its own. Together they pull continuously downward. The engineering constraints described in earlier sections were hard. They were also indifferent. Physics does not have a political agenda. The gravity well of money and attention is something different. It is shaped by choices, by cycles, by what captures public imagination and what loses it. And that means it could, in principle, be changed. Whether it has been and whether it is being changed now is where the accounting gets harder still. The engineering constraints described in earlier sections were indifferent. Physics does not negotiate. But beneath those constraints sits something more intimate. Something that cannot be solved with better alloys or more efficient engines. The body itself. Astronauts are among the most physically prepared people on Earth. They train for years. They are tested in environments designed to push them toward their limits. None of that changes what deep space does to a human body. The moon does not care how fit the crew is. The biology runs on rules older than any space program, and those rules were written for a different world entirely. Radiation is the first problem, and it begins before the spacecraft touches the surface. The International Space Station orbits about 400 kilometers above Earth. At that altitude, Earth's magnetic field still provides substantial protection. It deflects most of the high-energy charged particles streaming in from the sun and from deep space. Astronauts on the ISS receive roughly 0.3 to 0.5 millisieverts of radiation per day, a millisievert being the standard unit for measuring biological radiation dose. That is higher than on the ground, but for missions of a few months, it is manageable. Beyond the Van Allen belts, protection nearly vanishes. The Van Allen belts are two zones of magnetically trapped radiation encircling Earth. Cross them, and you leave the shield behind. In deep space, astronauts face two distinct threats. Galactic cosmic rays, which are high-energy particles streaming in from outside the solar system, arrive continuously. Solar particle events, which are intense bursts of radiation thrown out during solar flares, and coronal mass ejections, arrive suddenly and unpredictably. The dose rate in deep space runs roughly 1 to 2 millisieverts per day under normal conditions, and substantially higher when the sun erupts. Over a few weeks, the cumulative dose climbs to the equivalent of several CT scans. That comparison is worth holding for a moment. A single CT scan is not harmless. Doctors use them carefully, weighing benefit against a small but real increase in cancer risk. Astronauts on a multi-week lunar mission are absorbing that exposure not once, but several times over, continuously, with no way to stop it. Radiation raises cancer risk over time. It damages bone marrow. It affects the central nervous system in ways researchers are still working to understand. The straightforward engineering response is to add shielding. But shielding requires mass. And mass, as earlier sections established, triggers the rocket equation penalty immediately. Every additional kilogram of shielding demands additional propellant to accelerate, which demands additional structural mass to contain the propellant, which demands still more propellant. The compromise reached on current mission architectures is practical, if uncomfortable. Designated storm shelters, small reinforced sections of the spacecraft, give the crew a place to retreat when solar particle events spike. Astronauts shelter there during solar storms and accept the elevated background dose the rest of the time. It is not a solution. It is a managed trade-off. Radiation is what space does to the body from the outside. Microgravity is what the absence of gravity does from the inside. The human body evolved in 1G. Every system, bone, muscle, blood vessel, vestibular apparatus is calibrated to operate under constant gravitational load. Remove that load, and the calibration drifts. On the ISS, without aggressive countermeasures, bone density falls at roughly 1 to 2% per month. The legs and back lose muscle mass quickly because they no longer have any load to resist. The cardiovascular system remodels as fluid, that gravity normally pulls toward the lower body shifts upward. The heart, working less hard to pump against gravity, gradually reduces its output capacity. These changes begin within days. A lunar mission involves several days of microgravity traveling out. Some days on the surface at partial gravity, then several days in microgravity returning. Even a 10 to 20 day mission is enough to measurably degrade balance, motor control, and orthostatic tolerance. which is the ability to maintain blood pressure when standing upright. That degradation matters enormously when the crew arrives at the moon and immediately needs to operate complex equipment in an environment with no margin for error. Exercise machines running continuously during transit slow the effects. They do not cancel them. Astronauts returning from ISS missions after 6 months often cannot walk unaided immediately after landing on Earth. They need time to readapt. The moon offers no readaptation period. The answer is stranger than expected. Arriving on the surface does not simplify the biology. It replaces one problem with a different one. Lunar gravity is about 1/6 of Earth's. A 90-kilogram person, roughly 200 pounds on Earth, weighs about 15 kilograms on the moon, around 33 pounds. That sounds liberating. In practice, the biomechanics are deeply counterintuitive. You're too light for normal walking, but heavy enough that a fall still hits hard. The Apollo astronauts discovered this firsthand. They could not walk normally. They adopted a loping, bounding gait, hopping forward with both feet, angling their bodies to maintain balance on uneven, dusty ground. They fell, multiple times, on multiple missions. Now add the suit. A lunar surface suit weighs more than 100 kilograms, roughly 220 pounds, plus the life support system on the back. The astronaut wearing it weighs around 80 kilograms. In 1/6 gravity, the combined system weighs less than it would on Earth, but inertia is unchanged. Inertia is resistance to changes in motion, and inertia depends on mass, not weight. When that tall, top-heavy stack begins to tip, it keeps tipping. The center of mass is high. The suit limits the range of motion needed to correct a fall. The surface is uneven and coated in a fine dust that offers inconsistent grip. An ankle broken on a lunar surface is not an inconvenience. It is a crisis. Medical care is minimal. The crew cannot call for help and expect a response in time. The moon is 384,400 kilometers away. Evacuation, if possible at all, takes days. And yet, as serious as these known problems are, a larger uncertainty sits beneath them. We have essentially no long-duration biological data for humans living at 1/6 gravity. None. The entire history of human spaceflight in orbit has given us 2 gravity data points. Earth, at 1G. Orbital platforms like the ISS, at effectively 0 gravity. Everything between those 2 extremes is unknown territory. Does 1/6 gravity slow bone loss compared to weightlessness, or stop it entirely? We do not know. Does it resolve the fluid shift problem, or merely reduce it? We do not know. What does extended time at 1/6 gravity do to the immune system, to brain structure, to aging, to fertility? We do not know. The crews of a permanent lunar base would not simply be explorers. They would be the first long-duration test subjects at a gravity level humanity has never lived in before. The data they generate would be new, not the application of existing knowledge. New knowledge, gathered at personal biological cost. Life support adds one more layer. It is the most unforgiving of all. Every kilogram of oxygen, water, and food that cannot be produced on the moon must be launched from Earth. Launch costs to low Earth orbit run into thousands of dollars per kilogram, with additional costs for the lunar leg beyond that. Carrying full consumable reserves for a long-duration crew quickly becomes impossible on a mass budget. Regenerative systems become mandatory instead. Carbon dioxide exhaled by the crew must be chemically scrubbed and converted back to breathable oxygen. Water must be reclaimed from humidity in the air, from sweat, from urine. Waste must be managed carefully. Every input and every output must cycle through the system continuously. Closed loops do not forgive small failures. A slow leak in a habitat wall quietly drains the air over hours or days. A subtle fault in the water recycling chemistry contaminates the supply in ways that may not be immediately detectable. A stuck valve in a carbon dioxide scrubber lets CO2 levels climb unnoticed until crew performance begins to degrade, and by then, the system is already behind. Repair windows on the moon are measured in days for resupply and months for hardware replacement from Earth. The crew must carry spare components, repair procedures, and the skills to execute those procedures correctly on systems they may never have failed before. There is no maintenance team arriving the next morning. Think about an aquarium ecosystem. Every organism and every chemical cycle dependent on the pumps, filters, and gas exchange running correctly. A single stuck valve in the wrong place can begin a cascade that threatens the entire tank before anyone notices something is wrong. A lunar habitat runs on the same logic, except the consequences of the cascade are measured in human lives and mission months rather than fish. A permanent slow countdown runs in the background of every imperfect life support system. The question is always whether the crew can locate the fault and fix it before the countdown reaches zero. The biology then is not a secondary problem layered on top of the engineering challenges. It is a second floor of constraints beneath the engineering floor, equally hard, in some ways harder, because the engineering constraints at least have known solutions. For some of the biological unknowns, we are still waiting for data that only actually missions can provide. And those missions have not yet happened. Now think about what is pressing against that habitat from the outside. The surface of the moon is not neutral ground. It is not empty space, not a benign vacuum that simply leaves things alone. From the moment any structure or suit touches the regolith and begins operating, the environment begins working against it. Every material, every seal, every electronic component faces a sustained attack from multiple directions at once. And unlike the biological and engineering problems inside the habitat, the attack from outside never pauses. Start with temperature. In direct sunlight, the lunar surface reaches roughly positive 120 degrees Celsius, around 250 degrees Fahrenheit. When the sun drops below the horizon and the 2-week lunar night begins, that same surface cools to approximately negative 170 degrees Celsius, around negative 274 degrees Fahrenheit. The swing between those two states is roughly 290 degrees Celsius. On Earth, an atmosphere distributes and cushions temperature change. On the moon, there is no atmosphere. Nothing buffers the transition. A surface in sunlight is absorbing direct solar radiation with nothing filtering it. A surface in shadow is facing the open cold of deep space, with nothing between it and the void. That thermal swing does not just feel extreme, it acts on materials like a slow, relentless hammer. Metals expand in heat and contract in cold. Plastics stiffen at low temperatures and soften in high ones. Seals harden and lose their grip. Solder joints, the tiny connections holding electronic components in place, experience repeated expansion and contraction cycles that fatigue them over time, producing hairline fractures that are invisible until they fail. A crack in a seal becomes a pathway for vacuum. A fatigued solder joint becomes an intermittent failure, then a permanent one. And this does not happen once. It happens every lunar day-night cycle, roughly every 29 Earth days, indefinitely. A structure on the moon that must survive a year faces more than 12 of these full thermal cycles. A structure intended to last a decade faces more than 100. Something else was happening. Even before the thermal cycles accumulate, the surface is already attacking through a different mechanism entirely. The Apollo crews noticed it within hours of landing. Every suit that went outside came back coated in fine grey powder. The regolith of the moon is not like soil or sand on Earth. On Earth, wind and water erode particles, rounding their edges over time. On the moon, there is no wind, no water, no erosion of that kind. The particles remain as they were shattered, sharp, jagged, glass-like grit at a scale the eye cannot see. Many grains are smaller than 50 micrometers, and under a microscope, their edges look like broken glass. The source's description captures it exactly. This is ultra-fine glassy grit. That grit gets into everything. It works into the joints of suits, grinding against the bearings and seals designed to allow movement. It scratches visors, reducing visibility over repeated EVAs. When astronauts track it into a cabin on their suits, it becomes airborne, irritating eyes and lungs. The human lung did not evolve to handle jagged glass particles of that size. Over short Apollo missions, this was an annoyance. Over weeks and months, it becomes a genuine health hazard and a maintenance burden. And the dust does not even need physical contact to cause problems. The lunar surface builds up an electrostatic charge from solar radiation and the solar wind, and the dust grains carry that charge. They cling to fabrics, visors, and surfaces electrostatically, in the same way static cling holds lint to clothing, except that the particles are abrasive and the surfaces they cling to are precision components. The longer a mission runs, the more accumulated dust degrades the systems it touches. Better airlock designs, filtration systems, and suits that remain docked outside habitats can reduce how much dust enters. But each of those solutions adds complexity, mass, and another category of potential failure. The micrometeorite problem is harder to manage because it cannot be filtered or docked around. On Earth, the atmosphere burns up small incoming particles constantly. The Moon has no atmosphere. Every particle that approaches the surface arrives at full velocity. Micrometeorites, particles often a millimeter or less in diameter, strike the lunar surface at tens of kilometers per second. That is faster than a rifle bullet by a significant margin. At those velocities, even a small particle carries enormous kinetic energy, concentrated in a tiny area. A direct hit on an exposed surface does not scratch it gently. It punches a small crater, chips material, and in a thin layer can puncture it entirely. Habitat walls, radiator panels, external fuel tanks, exposed equipment, and suits are all in the line of fire continuously and without warning. A micrometeorite does not announce itself. There is no weather system to track, no season that concentrates the risk. The bombardment is simply the permanent background condition of existing on an airless body. Two protection strategies exist. The first is a Whipple shield, a thin outer layer positioned some distance from the main wall. When a high-velocity particle strikes the outer layer, it shatters, spreading its energy across a wider area before reaching the main structure. The particle that arrives at the inner wall is a dispersed cloud rather than a single concentrated projectile. The physics work, but the shield itself adds mass and complexity, and every kilogram added to a habitat that must be launched from Earth carries a price the rocket equation does not discount. The second strategy is to pile regolith over habitat roofs and walls, using the Moon's own material as natural shielding. This works without launching mass from Earth, but it requires infrastructure and machinery to move and place the material, and it cannot protect exposed equipment, radiators, and suits during EVAs. Neither solution eliminates the risk. Both manage it to an acceptable level while adding their own engineering demands. The suit, operating in all of this, is not protective gear in any ordinary sense. It is a personal spacecraft. The difference matters. Protective gear is designed to reduce harm from a specific threat. A helmet protects against head impact. A fire suit resists high temperatures. A personal spacecraft must simultaneously manage every threat an environment poses, and the lunar environment poses many of them at once. A next-generation lunar EVA suit must hold an internal pressure of 30 to 50 kilopascals, the range at which blood remains liquid at body temperature. Without that pressure, the fluids in a human body would begin to behave as if they were boiling. The suit must supply oxygen continuously and scrub carbon dioxide before it accumulates. It must regulate temperature, actively cooling the body during exertion and adding heat during rest in shadow. Because lunar temperatures vary by nearly 300 degrees, across a single day and shade arrives instantly. It must carry communications, block ultraviolet radiation, and some portion of the particle radiation environment, and still allow the wearer to walk, bend, crouch, grip tools, climb, and work for hours. The mass of a fully equipped lunar EVA suit, including life support, runs approximately 80 to 90 kilograms, about 175 to 200 pounds. In lunar gravity, the suit weighs far less than it would on Earth, but inertia does not change with gravity. A 90-kilogram suit resists acceleration and deceleration exactly as much on the Moon as it would anywhere else. Stiff gloves injure hands over repeated EVAs. Joint resistance in the suit's shoulders and hips causes fatigue. The high center of mass created by the life support pack changes balance in the 1/6 gravity environment where the body is already working against counterintuitive physics. A fall in a suit like this is a serious event, and the design target for next-generation suits is not a few hours of EVA. It is 8-hour EVAs, repeated day after day with minimal maintenance and limited spare parts. A suit failure during an EVA is immediately life-threatening. There is no slow version of that failure mode. Not backup protective equipment. A single-person spacecraft, and the only one available. Duration transforms all of this. Apollo missions ran hours, a few days at the outer edge. Engineers designing Apollo suits and equipment were designing for a short burst. A crack that might not fully propagate in 3 days will propagate over 90. A filter that would clog slowly over a week becomes a critical failure over 6 months. A seal that sustains 10 thermal cycles holds very differently from one that sustains 200. Think about the difference between spending a weekend camping outdoors and moving outside permanently for a year. The weekend camper can tolerate a damp sleeping bag, a temperamental stove, shoes that rub slightly. Those tolerances are manageable for 2 nights. The person living outside permanently faces those same tolerances, compounding every single day until what was minor becomes structural. The lunar surface operates on the same logic. Small acceptances made for short stays become mission-defining vulnerabilities over long ones. A slow leak that registers as a minor alarm over 3 days becomes a countdown over 90. Dust accumulation in an airlock that requires a few extra minutes of cleaning in the first week requires an hour by the 6th month. A suit bearing worn to 80% of its design life in a 2-week mission is a replaced component. That same bearing, on a mission with no replacement parts, is a schedule your evacuation problem. The lunar surface offers no easy mode after the hardware is in place. It does not become familiar. It does not become predictable. It attacks continuously, with new mechanisms layering on top of each other the longer the exposure continues. And the surface hostility is only the 3rd floor of the structure. Beneath it still sit the biology and the engineering that preceded it. The moon is asking every system, living and mechanical, to perform perfectly under sustained attack. Far from any repair shop, with the clock on everything running at the same time. Ask how any of this actually stays connected, and you find another layer of constraint waiting underneath. The signal that carries every command, every voice transmission, every data packet between Earth and the moon travels at the speed of light. That sounds reassuring. Light is fast. Radio waves travel roughly 300,000 kilometers every second. At that speed, covering the 384,400 kilometers to the moon takes just over a second. The round trip comes back in about 2.5 seconds. 2.5 seconds sounds like nothing. It is not nothing. It is the end of real-time control. Think about what that loop actually means in practice. You press a command, you wait. The signal arrives. The machine responds. You wait again. You see the response. You adjust. You wait again. For anything requiring fast, reactive decision-making, that loop is already too long. Landers cannot be joysticked from Earth during final descent. The terrain changes too fast. Unexpected obstacles appear and disappear in less time than a round-trip signal allows. Onboard guidance systems handle most of the descent autonomously, with human crews able to intervene only at limited points, always with that delay baked in. The ground team watches. They cannot steer. And that is only the first communications problem. The moon is tidally locked. The same face always points toward Earth. It never rotates relative to us in any way that would reveal the other side. Half the moon, the far side, is permanently radio dead to Earth with no infrastructure in place. There is no line of sight. No signal gets through. A lander or base on the far side requires relay satellites to exist before it can communicate at all. Those relays can orbit the moon in low lunar orbit, or they can sit in halo orbits around the Earth-Moon L2 point, a gravitational balance region roughly 65,000 kilometers beyond the moon on the far side. Either way, each relay is another launch, another spacecraft, another potential failure point, another system that must work before anything below it can function. Then the data shifted. Even the lunar orbits themselves cannot be trusted to stay where they are. The moon's gravity field is not smooth. Ancient impacts buried enormous concentrations of dense material, called mascons, short for mass concentrations, unevenly beneath the surface. Those buried masses pool on orbiting spacecraft, with slightly more gravitational force than the surrounding terrain, tugging orbits out of shape over time. An orbit that is correctly placed on Monday drifts by tens of meters over following days, and hundreds of meters over following weeks. Low lunar orbit, which is exactly where detailed mapping and pre-landing staging operations need to happen, is especially sensitive to this effect. It is like surfing a slightly warped gravity field that keeps trying to kick you off. Meters of drift at the wrong moment can shift a descent corridor from a safe plane to a crater wall. Solutions exist: accurate gravity maps, constant orbital tracking, and regular correction burns. But each correction burn costs fuel, and every kilogram of fuel is a kilogram that arrived at the moon through the full weight of the rocket equation. Add the Earth side of the link, and the constraint tightens further. Earth talks to spacecraft at the moon, at Mars, at Jupiter, at the outer planets and beyond, through a network of large radio antenna installations. The largest dishes stretch up to 70 meters across. That infrastructure is already running near capacity, dividing its time and bandwidth among Mars orbiters, Mars rovers, planetary probes, and various science observatories. A crewed lunar mission demanding high data rates for continuous video, telemetry, and voice communications requires priority scheduling. When multiple crewed missions begin operating regularly, that shared network becomes a bottleneck. There is a single highway serving every destination in the solar system simultaneously. Add enough destinations and the highway fills. The result of all of this: the signal delay, the far side blackout, the orbital drift, the bandwidth ceiling, is that autonomy around the moon is not optional. It is the only architecture that works. Landers must detect hazards and abort or redirect without waiting for a human command from Earth. Habitat power systems must reroute around faults before a crew notices anything is wrong. Life support systems must identify failures, isolate them, and begin corrections faster than the round-trip signal would allow. Rovers must navigate local terrain without streaming every decision to a ground controller. Every critical system must be capable of making the right call locally, in real time, in an environment where mistakes cannot be walked back. These are not simple programs. They are effectively autonomous control systems operating where errors can be fatal. The consequence is more code, more sensors, more avionics, more redundancy at every layer of the software stack, and more verification, because bad landings cannot be patched the way a phone application can. Every extra line of code is one more place where a rare, previously unseen interaction between two systems can produce an unexpected output. The testing regime requires simulations, hardware-in-the-loop setups, and repeated fault injection scenarios where engineers deliberately introduce failures to see whether the system responds correctly. Getting that verification right is its own long engineering program. The connective tissue has walls of its own. And beneath the communications architecture sits the propulsion question, which turns out to be its own kind of trap. After decades of spaceflight, fuel might seem like a solved problem. It is not. Chemical rockets are already close to their thermodynamic ceiling. The best propellant combinations available, refined kerosene burned with liquid oxygen, or liquid hydrogen burned with liquid oxygen, have been optimized over generations of development. A high-performance hydrogen-oxygen engine firing in vacuum achieves a specific impulse, the standard measure of fuel efficiency, in the mid-400-second range. Specific impulse measures how much thrust an engine produces per unit of propellant consumed per second. Mid-400 seconds is close to the physical limit of what chemical combustion can deliver. Roughly doubling that efficiency to around 800 seconds requires nuclear thermal propulsion or more exotic technology. No new chemical propellant is going to close that gap. Chemistry has found most of its room. The delta V requirement for a full lunar mission, the total velocity change needed from launch to return, sits between 10 and 11 kilometers per second. That figure does not move. It is set by orbital mechanics and the moon's distance. With engine efficiency near its ceiling and the delta V requirement fixed, the remaining levers are staging, mass fractions, and mission design. Engineers work those levers relentlessly, but there is no shortcut through the underlying physics. Liquid hydrogen is the most efficient chemical fuel available. It also requires storage at roughly 20 Kelvin, which is negative 253 degrees Celsius, negative 493 degrees Fahrenheit, about 20 degrees above absolute zero. Keeping hydrogen that cold across days or weeks of emission through exposure to sunlight, vibration at launch, shadow, and time requires thick insulation, complex tank designs, and sometimes active cooling systems. Without those, the hydrogen slowly boils away, reducing available propellant before the mission is complete. Every kilogram of insulation needed to prevent that boil-off is a kilogram not available for payload or safety margin. Storable propellants exist that avoid the cryogenic problem entirely. The Apollo lunar module used hypergolic propellants, liquids that ignite spontaneously on contact with each other, requiring no spark or ignition system. Reliable, proven. But hypergolics are extremely toxic and corrosive. Handling them near a crew habitat demands elaborate safety procedures. They are dangerous in ways that complicate the architecture of everything around them. Green propellants, being developed as safer alternatives, often deliver lower performance or introduce new engineering complications around freezing points, boiling points, and material compatibility. No single propellant is simultaneously high performance, non-toxic, and long-term storable. That combination does not exist. The most appealing long-term solution is making propellant on the moon itself. Lunar polar regions, permanently shadowed craters where sunlight never reaches, almost certainly hold water ice at temperatures below negative 200 degrees Celsius, negative 398 degrees Fahrenheit. In theory, the process is straightforward. Mine the ice, melt it, electrolyze it into hydrogen and oxygen, then liquefy and store both gases for use as propellant. In theory, it solves the resupply problem permanently. In practice, what that description actually requires is a mining operation and a chemical processing facility running continuously in constant darkness, vacuum, and extreme cold. It needs machines that can dig through frozen regolith without jamming, hardware that resists dust infiltration and thermal stress, continuous power to run the electrolysis and liquefaction systems, storage that prevents boil-off once the gases are produced. It is not a gas station on the moon. It is a full refinery operating in one of the harshest environments humans have ever attempted to use industrially. Nuclear thermal propulsion would change the equation. A nuclear thermal engine heats propellant using a reactor rather than burning it, and can roughly double the specific impulse of a chemical engine. Nuclear surface reactors could also provide steady power through the 14-day lunar night, when solar panels produce nothing. The technical case is strong. The barriers are not technical, they are political. Public concern about launch accidents, radioactive fallout, and weapons applications slows regulatory approval substantially. Approval takes years. Some partner nations will not agree to nuclear launches at all. A technology that works in engineering terms can remain unavailable in operational terms for a very long time. Propulsion, then, is not a solved problem. It is a choice between kinds of pain. Near-limit chemical performance that leaves almost no margin. Cryogenic storage difficulty that penalizes every kilogram of insulation required. Toxic hypergolics that complicate everything around them. An ISRU refinery that is theoretically ideal and practically brutal. Nuclear options that are technically ready and politically constrained. The entire lunar architecture must be built around whichever of those pains the mission chooses to accept. The connective tissue does not simplify the structure above it. It adds its own hard floor underneath everything else. And the question of what keeps all of this running once it lands, where the power comes from through 2 weeks of unbroken darkness, has its own answer waiting. The moon keeps time differently than Earth does. One full cycle from sunrise to sunrise takes roughly 29.5 Earth days. About half of that is sunlight. About half of that is darkness. At the equator, a single lunar night lasts close to 14 Earth days straight. Not an overcast afternoon, not a long polar winter with some twilight at the edges. Total darkness. The sun drops below the horizon and does not come back for 2 weeks. Solar panels produce nothing during that time, not less, nothing. Think about what that means for a base that has to keep humans alive. A modest habitat running lights, air circulation, life support, and basic systems draws something in the neighborhood of 10 kilowatts continuously. That is not a research campus or a manufacturing facility. That is the bare floor of survivability. Across 14 days of darkness, which is 336 hours of continuous night, keeping that floor powered requires roughly 3,360 kilowatt hours of stored energy. That is the bare minimum, with no safety margin, no emergency drawer, no heaters running on equipment parked outside. Add a reasonable safety margin, add heater loads and inefficiencies and the occasional crisis drawer. The realistic energy budget for surviving a single lunar night climbs past 10,000 kilowatt hours without much effort. Now comes the problem. Modern batteries store roughly 200 watt-hours per kilogram. That is the current state of the art for high-performance lithium-ion cells. At that density, 10,000 kilowatt-hours of storage requires around 50,000 kilograms of batteries. That is roughly 110,000 pounds. For context, that is heavier than a fully loaded semi-trailer and its cargo multiplied by several times over. Shipping that battery mass from Earth is not a logistical challenge. It is a structural impossibility for any near-term outpost. Even the bare minimum number, 3,360 kilowatt hours at no safety margin, requires around 17,000 kilograms. Still roughly 37,000 pounds. Still several times the mass of a lunar lander's entire payload capacity. The math does not work, not barely, not with clever optimization. Batteries alone cannot carry a lunar base through the night. But here's where it gets strange. The moon does have places where the sun almost never sets. Near the poles, certain ridges and crater rims sit at angles where sunlight grazes across them through nearly the entire lunar year. The geometry of the terrain keeps them illuminated, while the rest of the surface cycles through darkness. Build solar arrays on those ridges, and the power problem begins to look more manageable. Near continuous sunlight means near continuous generation. The 14-day blackout largely disappears for the arrays themselves. Except the water ice that makes a lunar base worth building is not on those ridges. It is at the bottom of deep, permanently shadowed craters, where sunlight has never reached. Temperatures inside those craters stay below roughly negative 200 degrees Celsius, because no sunlight ever arrives to warm them. The ice has been sitting there, preserved in cold storage, for billions of years. So the base cannot be in one place. The solar arrays go up on the sunlit ridges. The habitats sit elsewhere, partly buried in regolith for radiation and thermal protection. The mining equipment operates down inside the shadowed craters. Those locations are not adjacent. They are separated by terrain, by temperature gradients, by hundreds of meters of hostile surface. The base becomes a power grid. Energy generated at the ridges must travel to where the work is. That means cables stretched across lunar terrain, or beamed power systems converting electricity to directed energy and back again. Every meter of cable is additional mass shipped from Earth. Additional hardware exposed to dust and micrometeorite impacts at every point along its length. Additional failure modes in a system where failure has no backup service provider. The infrastructure spreads across a hostile landscape, and every node in it is a weakness. There is a second side to the power problem that is easy to miss. It is not just about generating energy. It is about getting rid of it. Every electrical system produces waste heat. On Earth, air and water carry that heat away. Wind passes over a warm surface and convection does the work. A cooling system pumps water through a heat exchanger, and the warmth dissipates into the air. The moon has no air. Convection does not exist. Heat has only one way to leave a surface on the moon. It must radiate away as infrared energy toward deep space. That requires radiators. Large, flat panels oriented toward the cold of deep space, designed to shed waste heat efficiently enough to keep equipment from overheating. For a base running significant power loads, those radiators are not small. They are a meaningful piece of infrastructure, and they are permanently exposed to the surface environment. Dust from passing landers and rovers settles on everything. Radiator surfaces are no exception. A thin layer of lunar dust is enough to reduce radiative efficiency measurably, because dust insulates rather than radiates. Over time, without cleaning, a radiator becomes progressively worse at the only job it has. And micrometeorites, which the surface receives continuously and without warning, can puncture or score radiator surfaces in ways that are difficult to repair and impossible to prevent. Think about cooling a powerful computer using only a passive heatsink that slowly gets coated in insulating dust and occasionally struck by high-velocity debris. The computer throttles down to avoid overheating, and you lose performance. On a lunar base, throttling down means reducing the capabilities of every system that produces heat, which includes most of the critical ones. So, what fills the gap that batteries and solar alone cannot cover? Fuel cells were part of the answer during Apollo. They combine hydrogen and oxygen chemically, producing water as a byproduct and generating electrical power in the process. They work well on short missions where the fuel can be carried from Earth. For a long-duration base, scaling them up means carrying or producing large amounts of hydrogen and oxygen continuously, which connects directly back to the in-situ resource challenges covered earlier. Radioisotope power systems, known as RTGs, take a different approach. They convert the heat from radioactive decay directly into electricity. They require no sunlight, no fuel, no moving parts. They run quietly for years. Rovers and space probes have used them successfully for decades. The limitation is output. A typical RTG produces somewhere between a few hundred watts and a few kilowatts, useful for instruments and backup systems. Not sufficient for the power demands of a human base. Small nuclear fission reactors solve the output problem. A compact surface reactor can produce tens to hundreds of kilowatts, day and night, independent of the sun entirely. Power through the 14-day blackout becomes a solved engineering problem, not an exercise in storage math. But reactors are heavy. They require radiation shielding for the crew, which adds more mass. They raise regulatory and safety concerns that have not been resolved by engineering. Launching a nuclear reactor from Earth has historically required extensive political approval processes that take years and involve multiple regulatory bodies. Some partner nations will not accept nuclear launches under any current framework. A technology that is technically mature can remain unavailable for operational reasons for a very long time. There is still another constraint the darkness imposes that goes beyond the base itself. Landers and rovers that sit idle through a lunar night face temperatures near negative 170 degrees Celsius. Hardware that is not actively heated begins to cold soak at those temperatures. Electronics experience thermal stress as materials contract. Solder joints, which are designed for a relatively narrow temperature range, can crack. Batteries lose significant capacity when cold soaked. Lubricants that flow freely at operating temperature become thick or freeze solid. Structural materials that tolerate normal temperature ranges become brittle at extremes. The engineers have two options. They can run survival heaters inside key components continuously through the night, drawing power even when the machine is doing nothing, just to keep the hardware alive. Or they can allow hardware to fully cold soak, and then design it to survive that repeatedly. Full cold soak tolerance requires extensive testing across hundreds of freeze-thaw cycles to verify that nothing fails in the 4th cycle or the 40th. Either way, the cost is real. Power or mass or testing time or reduced reliability confidence. Every design decision on a lunar base eventually runs through one of these constraints. Power for the night, heat rejection from the base, thermal survival for equipment left outside. These are not problems at the edges of the design. They are recurring requirements that sit near the center of it. And the question of who will actually live inside that base and what extended time in that environment will do to them over months and years is a layer the hardware cannot answer on its own. The hardware sitting at the center of all of it runs on software. That layer is invisible from the outside. It generates no heat signature, casts no shadow, adds no visible mass. But it is the layer where every other constraint eventually arrives to be managed. And it is the layer that has changed more dramatically than any other since Apollo. The Apollo guidance computer ran at roughly 1 megahertz. It had about 2 kilobytes of random access memory. That is not a misprint. 2 kilobytes. Roughly the amount of data stored in a short text message. Engineers who worked on it could, with effort, hold nearly its entire behavior in mind. They could trace a fault from symptom to cause through a system small enough for a human brain to navigate. The software was constrained, and that constraint was, in its own way, a form of safety. Modern spacecraft fly nothing like that. A current smartphone runs billions of instructions per second and carries gigabytes of memory. Flight computers for modern lunar vehicles are not smartphones, but they operate in the same universe of capability. More powerful by orders of magnitude. And that is when the pattern broke. That power does not make the software safer. It makes it harder to understand. Modern flight software does not exist as a single program. It exists as layers, an operating system at the base, middleware handling communication between components, drivers translating sensor signals into usable data, control logic managing guidance, navigation, and propulsion, redundancy management watching for faults, and switching between backup systems. Each layer is built by a different team, tested against its own requirements, and then integrated with the others. Each layer creates new failure modes, not from carelessness, from complexity itself. Every feature added to the vehicle adds code. Autonomous landing algorithms require cameras, LiDAR sensors, image processing, and the logic to interpret what the sensors see and act on it in real time. LiDAR is a ranging system that fires laser pulses and measures the time it takes for them to return, building a 3-dimensional map of the surface below. Adaptive life support requires constant sensor reading, threshold monitoring, and fault isolation. Automated power management routes electricity between sources and loads, depending on what the vehicle is doing and what has failed. Each of these systems adds tens of thousands of lines of code, sometimes hundreds of thousands, sometimes millions. And proving that millions of lines of code behave correctly in every possible situation is not difficult. It is impossible. The available approaches are aggressive testing, scenario simulation, formal mathematical methods where they can be applied, and redundancy so that a fault in one path does not propagate to the whole. These approaches find most problems, but a software failure during flight is not like a laptop freezing. You do not reboot and shrug. A crash, a lockup, a race condition where two processors compete for the same resource at the wrong moment. A pointer bug where the software reads memory it was not supposed to read. A mishandled sensor reading that passes a bad value into a guidance calculation. Any of these, at the wrong moment, can cascade into a decision the vehicle should not make. There is no IT support call. There is no undo. Apollo 11 demonstrated this in a way that very nearly ended the mission. On July 20th, 1969, during the final minutes of powered descent toward the lunar surface, the guidance computer began generating alarms. The 1202 alarm, then the 1201. Both indicated executive overflow. The computer was being asked to do more than it could handle simultaneously, and was dropping lower priority tasks to keep the critical ones running. The system was technically correct. It was managing the overload exactly as it had been designed to. But the crew and mission controllers in Houston had never seen those alarm codes in a landing context. They had to decide in seconds whether to abort or continue. They continued. The landing succeeded. But the margin was not comfortable, and modern systems can generate many more alarms than Apollo's could. Poorly designed alarm systems create what engineers call alarm storms. A single fault triggers a cascade of warnings from every system that depends on the faulted one. Dozens of alarms within seconds. The real cause is somewhere inside that cascade, but separating it from the downstream effects requires analysis. The crew may not have time to perform. The astronaut reading those screens may be wearing a bulky pressure suit with stiff gloves that make interface work awkward. They may be hours into an EVA, fatigued, dehydrated, managing the disorientation of partial gravity, interface engineering, the layout of buttons, the hierarchy of information on screens, the flow of procedures, the training that makes it second nature, is not a cosmetic concern. It is safety-critical infrastructure. Bad interface design creates confusion during exactly the moments clarity is most needed. And then, there is a dimension Apollo never faced at all. In the 1960s, the only signal reaching a lunar spacecraft came from NASA ground stations. The idea of an adversary sending spoofed commands to an Apollo capsule did not arise as an operational concern. That world no longer exists. More nations and more companies now operate in cislunar space. The communications environment is shared, contested, and monitored. A spoofed command, one that appears legitimate but was not sent by the flight team, can cycle a valve at the wrong moment. It can misalign an antenna, cutting the crew off from ground support. It can trigger an engine burn at the wrong phase of the mission. The consequences do not scale with the size of the interference. A single malformed packet, believed and acted upon, can lose a mission. Cosmic rays already force engineers to use error-correcting codes in spacecraft memory. A high-energy particle passing through a memory chip can flip a stored bit from 0 to 1 or 1 to 0. Error-correcting codes, mathematical redundancy built into how data is stored, catch and correct single-bit flips before they propagate. Radiation-tolerant hardware uses materials and circuit designs that resist the damage. These protections exist because the radiation environment of deep space demands them. Cybersecurity demands a different but overlapping set of protections. Encryption. Strong authentication, meaning proof that a command actually came from the authorized source. Key management. The secure storage and rotation of the cryptographic credentials that make authentication possible. Secure boot. Verification that the software running on the flight computer has not been tampered with. These are not optional additions. They are required layers in an environment where the communications link is an attack surface. None of these layers is free. Each adds code, each adds complexity, each adds verification burden. That burden is the hidden cost that determines schedules more than almost any other factor. For every line of code that actually flies, many more lines exist in test harnesses, simulators, and analysis tools that never leave the ground. Hardware in the loop testing runs the actual flight computer connected to simulated sensors and actuators, feeding it synthetic data that mimics every phase of the mission repeatedly, looking for rare timing bugs that only appear under specific conditions. Engineers inject faults deliberately. They cut simulated data lines, they flip bits, they drop packets. They ask, what does the system do when this sensor spikes at exactly the moment a reboot is in progress during a power transient? Most of the time, the answer is, it handles it correctly. Occasionally, the answer reveals a state the software was never designed to reach, a condition that occurs perhaps once in a million executions. Under normal testing frequencies, that condition might never appear. Under hardware-in-the-loop testing running thousands of simulated missions, it surfaces. That bug is then fixed. The fix requires rewriting code. The rewrite requires retesting everything the changed code touches, because a fix in one place can introduce a failure somewhere else. The retest requires rerunning the verification suite. The full cycle takes weeks. From outside the program, that cycle looks like a launch slip. A schedule that was supposed to hold, failing to hold. Slowness. From inside, teams found a fault that would have been unacceptable in flight, and eliminated it before it could matter. The slowness is the safety. Not despite the care. Because of it. The iceberg image fits here. What a launch represents above the surface is a vehicle, a crew, and a date. What sits below the surface is an accumulated mass of test runs, code reviews, fault injections, scenario simulations, and edge case hunts that no one outside the program ever sees. The visible part is the smaller part. The invisible part is what makes the visible part survivable. Software does not announce its failures in advance. It does not wear down visibly, the way a seal degrades or a bearing wears. It waits for the exact combination of inputs that exposes the flaw, and then it fails completely and immediately. In an environment with no rescue, that profile makes the hidden verification work not optional overhead, but the foundation the mission stands on. And underneath all of it, the question of who will actually operate these systems under real conditions, fatigued and suited and far from any help, has no engineering answer on its own. That question about who operates these systems under real conditions opens into something the technical layers alone cannot answer. The hardware has constraints. The biology has constraints. The software has constraints. But every mission also exists inside a legal and scientific framework. And that framework has its own kind of gap, quieter than a failed valve or a missed orbit, but just as capable of stopping a program cold. Start with the law. The Outer Space Treaty, signed in 1967, establishes one foundational principle: no nation can claim the moon as sovereign territory. That was meant to prevent the moon from becoming another disputed colonial frontier. And in that narrow sense, it worked. No nation has planted a flag and declared ownership. But the same principle that prevents conquest also makes long-term investment deeply awkward. Here is the problem. If you are a company preparing to spend $1 billion building infrastructure on the lunar surface, you will want to know that infrastructure is protected. You will want something like a property title, a guarantee that a second operator cannot land next to yours, damage your equipment, and face no legal consequence. On Earth, frameworks for that exist. On the moon, they do not. Not clearly. Not in any form a contract lawyer can point to. And property is only the beginning. Physical coordination questions have no global framework either. How far apart must two landers be to avoid one plume contaminating the other's instruments? Who allocates radio frequencies when a dozen missions are transmitting simultaneously? If one company's regolith-moving operation blasts debris onto a neighbor's solar panels, what is the remedy? On Earth, air traffic control handles the first kind of problem. Maritime law handles the second. Road rules handle the third. On the moon, near zero. Most current coordination between programs is informal. Bilateral agreements between two parties who happen to be talking. Nothing systemic. But here is the inversion. The technology is ahead of the law. Building a lunar lander is now genuinely achievable by a mid-sized aerospace company with the right investors. Writing a treaty that 190 nations trust enough to ratify is, by comparison, the harder problem. Governance lags well behind the technology. That inversion is new. For most of spaceflight history, the diplomats and lawyers were well ahead of the engineers. Not anymore. And the tension deepens when resources enter the frame. Some national laws, including recent legislation in the United States, permit companies to own and sell resources they extract from space. Mine the ice, own the water. That logic has legal standing in some jurisdictions. In others, it violates a different principle from the same treaty era. That space is the common heritage of all humankind, not a resource pool for whichever company arrives first with a drill. No global agreement bridges those two positions. The debate echoes old arguments from maritime law and deep-sea mining rights. Those arguments took decades to partially resolve on Earth. They are now 384,400 kilometers away and moving faster. Dual-use technology sharpens the tension further. A communications relay on the lunar surface can support scientific data transmission. It can also support surveillance. A radar system mapping regolith composition can provide geological data. It can also track orbital assets. Power beaming lasers designed to transfer energy between surface installations have potential weapons applications that defense agencies are not ignoring. Every installation gets evaluated through a security lens, simultaneously. The boundary between peaceful and strategic use blurs with each new capability. Space lawyers and policy experts are now mission-critical personnel in ways that propulsion engineers at their drawing boards rarely consider. The scientific framework surrounding these missions has its own kind of gap. Not a legal one. A scale one. Think about what Apollo actually accomplished on the lunar surface. 6 landings. 12 astronauts who walked. Total surface time across all 6 missions. Roughly 80 hours. Not 80 hours per mission. 80 hours total across the entire program. Roughly 3 days of cumulative human presence on the moon. Total returned material. Approximately 382 kilograms, about 842 pounds of rocks and soil. Precious samples, studied intensively for half a century, still yielding new information. but the moon is approximately 3,400 kilometers across. Most of it has never been touched. Not sampled, not drilled, not visited by anything with instruments. Modern lunar science does not look at that number and feel satisfied. It looks at that number and sees an almost entirely unread archive. The moon acts as a recorder for the whole solar system. That is not a metaphor. Regolith builds up over billions of years from micrometeorite impacts and continuous solar wind exposure. The material accumulates in layers, each layer encoding conditions at the time it was deposited. Isotope ratios, meaning the specific mix of chemical variants of hydrogen, oxygen, and noble gases locked into the grains, carry information about solar activity across geological timescales and about how material moved through the early solar system. Reading that record requires clean sampling, uncontaminated drills, temperature-controlled storage from the moment of collection, and clean Earth laboratories. It requires not scooping, drilling, and it requires going to many places. Ancient highlands, where the crust has been stable since the earliest era of the solar system. Younger volcanic plains, where lava flooded basins and reset the record. Polar regions, where ice and ancient deposits interact. Deep impact craters, where excavated material comes from far below the surface. 1 or 2 landings cannot answer those questions. A network of missions is needed. Not a program, a network. The science that remains vastly exceeds the science already done. Apollo was not a beginning that was followed by a pause. It was a first narrow cut into something orders of magnitude larger. One specific opportunity captures that scale clearly. The far side of the moon, permanently turned away from Earth, is one of the quietest radio environments in the inner solar system. Earth generates an enormous amount of radio noise, broadcasting, telecommunications, radar, satellite signals. All of that noise washes over the near side of the moon and over every ground-based radio telescope on the planet. The far side is shielded from it. That shielding enables something almost impossible to achieve from Earth. Low-frequency radio astronomy, at wavelengths of tens of meters, can probe a period called the Cosmic Dark Ages. This is the era before the first stars formed, when space was filled primarily with neutral hydrogen gas and no light sources existed yet. The signal from that era is incredibly faint and lives at exactly the frequencies that Earth's radio environment drowns out. From the far side of the moon, with the bulk of the moon blocking terrestrial interference, those frequencies become accessible. Arrays of antennas spread across kilometers, requiring robust power and thermal survival across the 2-week lunar night, could open that window. The engineering challenge is serious, but the science on the other side is not incremental. It is the universe before stars existed. That reframe matters. The moon is not simply a destination in these programs. It is a scientific instrument. An instrument that only a functioning cislunar architecture with reliable power and communication infrastructure and the ability to deploy and maintain kilometer-scale arrays can actually build and operate. The science does not come before the infrastructure. The infrastructure makes the science possible. And underneath all of that, the governance frameworks, the contested resource rights, the scale of scientific ambition, the network of missions, that none of this reduces to a single launch or a single budget line. The legal vacuum that surrounds every billion-dollar hardware decision, all of it accumulates into something that the engineering flaws alone could not reveal. The hardest parts of returning to the moon may not be the ones that show up in a design review. The reusability revolution and the economics behind it are only beginning to change what any of this can actually cost. That shift in economics has been happening quietly, underneath all the other problems, for the better part of a decade, and it changes something fundamental about what a return to the moon can actually look like. For most of the space age, the cost of reaching orbit was measured in skyscrapers. A single Saturn V launch ran hundreds of millions of dollars at the time. In today's money, that figure exceeds $1 billion per flight. Every kilogram of hardware launched to the moon carried that price tag embedded in it. The architecture was built around it. You launched once. You used everything. You left nothing behind. The economics of disposability shaped every design decision from the ground up. That has begun to change. Partially reusable rockets can now reach low Earth orbit, for a few $1,000s per kilogram. That number is still falling. The difference in what it means is not incremental. An economy where launching your body weight to orbit costs roughly what a high-end sports car costs is structurally different from one where it costs as much as a building. Things that were once simply impossible become merely very expensive, and things that were very expensive become survivable at the program level even when individual missions fail. That last part is the quiet revolution. Government agencies no longer have to build every lander themselves. They can buy rides on commercial vehicles. Small companies can design specialized landers for specific missions. A failure destroys hardware and delays a timeline, but it does not end the program. The architecture begins to look less like a once-per-decade mega mission and more like a logistics market. Launches happen with higher frequency. Costs spread across more flights. Fixed infrastructure overhead, the ground teams, the mission control systems, the supply chains, gets amortized across a fleet rather than a single vehicle. Think about how aviation changed when it moved from one-way ships to aircraft that flew the same route hundreds of times. An ocean liner built to cross once and never return concentrates everything into a single voyage. An aircraft that flies a route hundreds of times spreads its cost across every crossing. The economics are not just better, they are a different category of economics. Reusable lunar landers operating between a lunar orbital station and the surface, refueled from depots stocked by commercial cargo flights, represent exactly that shift applied to cis-lunar space. None of that infrastructure exists yet, but it is being planned. Gateway-style orbital stations, propellant depots, relay satellites, orbital tugs. Each piece is a prerequisite for the next. The architecture has a name now: cis-lunar. The space between Earth and the Moon, treated as an operating environment rather than a gap to cross as quickly as possible. And something else was happening in parallel. All of that infrastructure, built to enable sustained human presence on the Moon, is simultaneously training for something farther out. Managing a lunar station teaches long-duration life support outside Earth's magnetic field. The same problem that a Mars mission will face for months at a time. Operating cis-lunar tugs and depots teaches orbital logistics at scales that interplanetary missions will require. Running distributed surface systems without the ability to call in a local repair team teaches the remote operations discipline that deep space demands. The Moon is close enough to reach in days when something goes wrong. It is harsh enough to force genuine deep space solutions rather than approximations propped up by proximity to Earth. It is not a stepping stone chosen arbitrarily. It is deliberately chosen because it is the hardest training environment that still allows rescue if everything fails. The distance matters here in a way that is worth sitting with. The Moon is roughly 384,400 kilometers away, about 30 Earth diameters. That number has appeared throughout this journey, but its weight lands differently at this layer of the problem. From low Earth orbit at around 400 kilometers altitude, an emergency return to Earth can happen in hours. That option does not exist on the Moon. If something serious goes wrong on the lunar surface, there is no rescue. There is no emergency evac. The mission is the rescue plan. That psychological reality is not a footnote to the engineering. It is an engineering input. Astronaut selection has shifted to reflect it. Physical fitness remains essential, but extreme psychological resilience now sits alongside it as a non-negotiable. The ability to function under chronic isolation, to manage interpersonal conflict in confined spaces over extended periods, to sustain performance when the environment is hostile in every direction and home is a long delay away. Analog training helps. Antarctic research stations, underwater habitat programs, months-long isolation simulations. None of them fully replicate the conditions, but they filter for the people who can tolerate what cannot be fully simulated in advance. Mental health support has been redesigned as engineering. Private communication time is scheduled. Conflict resolution procedures are written into crew protocols. Cabin layouts are planned around the need for personal space within structures that cannot afford to be large. Schedule design balances task density against psychological fatigue. These are not soft considerations added after the engineering is done. They are constraint inputs that shape every habitat design from the earliest planning phase. The public dimension of the psychology is harder to engineer. Cultural familiarity has done something unexpected to the moon. Decades of films, games, and images have turned it into background scenery. The felt wonder that made Apollo a civilizational moment has, for many people, faded into something closer to familiarity. Voters respond to firsts. A repeat mission, even one that is objectively harder and more ambitious, does not generate the same emotional response even when it represents a far deeper commitment of capability and resources. From a distance, the moon is a dead, airless rock. That is not wrong, but it is incomplete. Making the case for why it matters requires a coherent answer. Science, resource access, survival preparation, developing the capabilities that could eventually let humanity exist beyond a single world. Without that coherent narrative, maintained through administrations and budget cycles, and the slow grind of years without visible progress, programs drift. They get delayed. They get descoped. They get cancelled. Public attention behaves like a physical input in these systems, not a background condition. It shapes what companies can sell. It shapes what programs survive. And human psychology runs on short timescales. Lunar infrastructure needs decades. That mismatch is the deepest constraint. Apollo compressed into roughly a decade because a political emergency supplied the attention and the resources simultaneously. A true cis-lunar system will take multiple decades to build. Those making funding decisions now will not see it completed. The people writing the policies, approving the budgets, launching the first missions, most of them will be gone before the staircase reaches its landing. That is not a failure of ambition. It is the nature of the timescale involved. Cathedrals in medieval Europe sometimes took 2 centuries to finish. The builders of the foundations never saw the spires. The work continued because each generation could see the progress made before them and add to it rather than starting over. Each generation of the lunar program needs visible wins along the way, not just distant promises, returned samples, landed hardware that survives a lunar night, a crewed descent that comes home, small compounding victories that make the next ask credible. Without them, the political support decays, and the long arc of accumulation breaks. No single breakthrough will suddenly resolve what has been laid out across this entire journey. Not a miracle propulsion system. Not a perfect international treaty. Not a single budget decision that unlocks everything downstream. Progress comes from many small improvements compounding together. Slightly more efficient engines, marginally cheaper launches, more durable suit joints, better recycling yields, more robust autonomous software. Each one is individually unremarkable. Collectively, they bend the curve. The moon stress tests all of it simultaneously. Not just the rockets, not just the astronauts, everything at once. Propulsion, life support, thermal management, software, communication architecture, power systems, governance frameworks, material science, human psychology, public narrative. A short mission can hide the weak spots in any of those layers. Sustained presence exposes all of them. That is not a bug in the design. That is the design. Apollo left something real. It left memory. It left museum hardware. It left 12 people who walked on another world and came home. It left data and samples that researchers are still working through. But here is what it did not leave. It did not leave a reusable rocket. It did not leave a refuelable lander. It did not leave a habitat that could survive a year. It did not leave a legal framework for what comes next. It did not leave a culture that knew how to handle a failed mission and continue anyway. Not a staircase. A single leap. A serious return to the moon means building that staircase now. Reusable launch vehicles, refuelable landers, repairable habitats, stable international agreements, a public and institutional culture that can absorb failure without abandoning the project. None of that was necessary for Apollo. All of it is necessary for a lasting presence. If humanity builds it, something changes in the question itself. The inquiry that opened all of this, why is it so hard to go back to the moon, quietly inverts. The difficulty was never evidence that the effort was misguided. It was evidence of how much still needed to be built. The moon is not the destination. It is the first rung, and once you can live there, the question that follows is not about the moon at all. It is about everything that comes next.